So we're starting to understand continuity here, and in the last video we mentioned an informal definition of what continuity means. Basically, the function has to be defined at that point, and there should be no breaks in the graph at that point. Or in other words, when you trace the graph out with your pen, you should not have to lift your pen from the paper at that value of a. Why don't we just look at some examples here? Why don't I just draw a little graph here? All right, so it doesn't really matter. Let me say this is 1. Maybe this is 4, 5. And this is the graph of some function, f of x. And my question is this. Is f continuous at x equals 1? Well, maybe before I even ask you this question, let's trace this graph with our pen. If I trace this out, why don't I just quickly grab another color here? If I trace this out, I'm not lifting my pen from the canvas here. But right here at 1, notice I have to lift my pen to keep going. So just from that, I kind of have a feeling that this function has some kind of problem at 1. And that's formally basically what that means is that it's not continuous there. So I'm continuing tracing on. I hit 4. We have a kind of a change in direction here, but I actually don't have to lift my pen from the canvas to keep going. So maybe 4 is a point that is okay. There's not really a problem there. And so that's kind of what it means to be continuous. Anyways, I'm proceeding along, but when I hit 5 here, notice again, I have to lift my pen from the paper to proceed. And then from then on afterwards, I don't have to anymore. So I kind of have an idea that in the places where I had to lift my pen from the paper are the places where it is discontinuous. Discontinuous just means not continuous. And every other number where I did not have to lift my pen from the paper will be a point of continuity. So is f continuous at x equals 1? No. Why? Because like I said, when we reached... actually there's 2 reasons why it's not continuous at 1. You remember, to be continuous at a number, it's like 1, the function has to be defined there, right? And notice here we have 2 open circles, which means there is no value for f of 1. So f of 1 is undefined. And right away, that means it's not continuous there. But for another reason, there's a break in the graph there as well, right? So it's not continuous there. You know what I'm going to do? I'm just going to change this a tiny bit. It won't affect anything. And I'm going to go like this. All right. The next question, I'm just going to cheat a little bit and go like that. Is this function continuous at x equals 2? Well, right now, unlike x equals 1, notice that when x is equal to 2, the function is defined there, right? I don't know. Why don't we can make up some numbers here if we really want to. So f of 2 is equal to 4, say, okay? So this is 2 comma 4. So f of 2 is defined, but the function is it continuous at 2 or not? Well, notice when I draw this graph here, I'm going all along fine here at 2, but then as soon as I hit 2, I got to jump up and then jump back down, right? So there is a break in the graph at 2, and therefore, even though the function is defined there, it is not continuous there. The next question is at 3, say, okay? Or let's say 4. Well, let's say 3, sure. Notice at 3, there's no dot, okay? You don't. Often we write dots just to emphasize that we're looking at that point, but it's really it doesn't matter if a person draws a dot there or not. The essential thing is that notice at 3 when I draw. Why don't I change color again just quickly? Before 3, I'm here, I'm at 3, and then I'm after 3 now. I did not have to lift my pen from the paper when I traced the graph from around 3 there, right? And that's exactly what it means to be continuous there. Just because there's no solid dot here, like I said, that's irrelevant. So yeah, it's continuous with 3. How about at 4? Well, at 4 here, we do, like I said, have a change in direction, but the function's defined there because there's a solid dot. Again, if the graph, let's say the graph looked like this. In other words, the solid dot wasn't drawn. That's irrelevant. The function is still perfectly defined there, and there is no break in the graph, so it is continuous. Now, when we come to the next number 5 here, notice at 5 we have a solid dot, and actually this solid dot we have to have it there because it means something important in this situation. It means that, let me ask you a question. What is f of 5? If you look at this graph, what is f of 5? It kind of is it going to be like this number, like 4? It looks like a little bit higher than 4 actually. Or will it be, say, maybe 1.5? So let's pretend this is like 4.2 or something. And 1.5 is right there. Is f of 5 equal to 4.2 or 1.5? Well, of course it's equal to 4.2, right? That's what that solid dot means. So we kind of need to have this solid dot here. Whereas a solid dot here or here is actually just optional. It's unnecessary. Okay, I got a little bit off topic there. All I wanted to say is that at f of 5, notice the function. That's my next question, by the way. Is f continuous at x equals 5? Well, the function's defined there, right? F of 5 is equal to this number 4.2. What about the left? Is there a break in the graph there? Well, there sure is. When I'm tracing my graph here, I reach here and then I have to lift all the way off the paper to keep going onwards here. So the answer simply is no, it's not continuous there because there's a break in the graph. Is that okay? So even if I asked like a question like this maybe, what about, is this function continuous at, say, I don't know, 4.9? Well, even let's just say 4.7. Who cares? Whatever. 4.7 would be somewhere around here, right? Let's look at the graph there. Look how nice, and there's no breaks in it. The function's perfectly defined there. You see? And that just means that, yes, it is continuous there. So really, if I were to ask you, which numbers is this function discontinuous for? The answer would be the only numbers in this entire domain here where this function is discontinuous at is at 1. That's a bad one because we have a break there. And it's not even defined there. At 2, that's a bad number because the function has a break there. And at 5, those are the only numbers at which this function is discontinuous at. Any other number, it doesn't have to be an integer like 1, 2, 3, 4, whatever. It can be a decimal or even, let's say, pi. Okay, pi is like 3.14. Is f continuous at pi? Well, there's no break there, and it's defined there. So it is continuous there. All right, so I think I beat that to death. What we got to do next now is actually get a proper definition of continuity. We have a good informal understanding of what it means, but now we need to actually get a mathematically proper definition of what continuity means, and then we'll see how to work some problems from there.